anytime a measurement is made or a calculation is made for the sake of prediction, especially, the number of significant figures in that number is important. And we find the students struggle with handling significant figures and have a wrong impression concerning the number of digits they should keep in their answers. So this is not by any means a technical or formal treatment. This is a simple and informal treatment of significant figures, and it's sufficient for high school. We have to talk first about what are significant figures. Significant figures, the term itself seems self-explanatory, but let's go ahead and lay it out in a different way. It's the number of digits in the correct amount of number places, not just decimal places, number places. And these digits are supposed to tell us something about the precision with which the measurement was made, or the precision with which a prediction can be made from the calculation. It is not by any means the number of decimal places alone. Because scientific notation has a bearing on significant figures, and significant figures also have a bearing on scientific notation, we're going to mention scientific notation briefly here. The way we achieve scientific notation is we take the number as it was written in standard notation, and we convert it into scientific notation by repositioning the decimal. We move it from wherever it was in the standard notation number to between the leftmost first and second digits, or the first and second digits on the left from the original number. While we're moving, we count the number of decimal places that the decimal is moved, and then that will tell us the power that we have to multiply, the power of 10 by which we have to multiply the new number, the number with the decimal repositioned. When you consider the number as it was in standard notation, zeros that showed up on the left of the first non-zero digit, those were not significant. And so moving from left to right, any zeros you hit before you hit your first non-zero digit, those are not significant zeros. However, if a decimal was showing the original number and there were zeros to the right of the first non-zero digit as you move from left to right, those zeros are significant. However, if there was no decimal point showing in the original standard notation number, then because there was no decimal point showing, it's assumed that the zeros that are to the right are just holding number places. You'll see what we mean in our examples in a second here. Let's talk about some examples. This first number, ask yourself how many significant figures are showing here. The decimal showing, and we start from the left and move to the right, and we haven't hit any non-zero numbers yet, and then we hit our 2. That's our first non-zero digit. That starts our counting for significant figures, and so that is 1, 2, 3, 4, 5 significant figures. That's how many should show up in our scientific notation, and they do. 1, 2, 3, 4, 5. But we've moved the decimal how many places? 1, 2, 3, 4 to get to this position between the first and second leftmost digits. We moved it 4 places, and what we're saying is it's as if we took this 2.0687 times 0.0001, that would get us back to our original number, but 0.0001 equals 1 times 10 to the minus fourth. So in scientific notation what we do is we take the part of the number that had the decimal moved in it, and we multiply it by the appropriate number of powers of 10. If we multiplied by that number of powers of 10, that would get us back to the original number. This number, notice the decimal is in the same position relative to the first non-zero digit we hit as we move from left to right, but since the decimal is showing and we have zeros out to the right, they count. So we're going to say that when we're counting significant figures, we have 1, 2, 3, 4, 5, 6, 7. 7 significant figures. They better show up in our scientific notation. Here they are. 1, 2, 3, 4, 5, 6, 7. But the decimal has been moved how many places? 4. So it's as if we took this 2.068700 times 0.0001. That would give us back our original number. But it is also equal to 1 times 10 to the minus fourth. So we put the times 10 to the minus fourth on this 2.068700. And that is our scientific notation version of this very same number in standard notation. Okay, here's a different example. How many significant figures do we see? Well, no decimals showing this time. So that means zeros to the right of the last non-zero digit are not significant. These two are not going to be significant figures. So we've got 1, 2, 3, 4, 5 number places occupied. That's 5 significant figures. And why are these 2 zeros sitting out here? Well, it's to push things over into the right number places. It's to tell us this 7 is not 7 ones, it's not 7 tens like 70, it's 7 hundreds. So the tens place is just held by the 0 and the ones place is held by the 0. But since there's no decimal place here, we assume that those zeros are sitting there holding a number place, but not representing numbers that we could measure, that were significant in the precision of our measurement or our prediction. So we have 5 significant figures, but the decimal has to move how many places? It has to move 1, 2, 3, 4, 5, 6, which is why our scientific notation number looks like this. Remember, a million, which is 10 to the 6th, times the 2.0687 would give us our original number, but a million is 1 times 10 to the positive 6, so I'll just put 10 to the positive 6 on this 2.0687, and I can reproduce the original number from there. Notice the relationship here that has bearing on significant figures. Those 2 zeros were not significant. Let's try a different example. If I just simply change that number by putting a decimal, what I'm saying is I was able to measure out to the ones place for precision. This is between 2,068,701 and 2,068,699. We're saying this number is correct out to plus or minus 1 in the ones number place. So that changes our number of significant figures. We're still going to move our decimal place 6 places. We still have to move it 1, 2, 3, 4, 5, 6 places, and that means we're multiplying by a million. Turns out, million times 2.068700 gets us 2,068,700. When I multiply 2.068700 times 10 to the 6th, I will reproduce my original number with the same number of significant figures. Finally, let's consider this one. Okay, the decimal showing. The zeros to the right of the last non-zero digit are significant. So now we've got even more significant figures. We've got how many? 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. They'd better show up in our scientific notation version. There they are, 1, 2, 3, 4, 5, 6, 7, 8, 9. But our scientific notation has the decimal just to the right of the leftmost non-zero digit, and multiplying by 10 raised to the 6th power gets us back to our original number. So you can see here how important significant figures are to scientific notation, and that scientific notation is a handy way to figure out how many significant figures there would be in the original number, because when we put things in scientific notation, we wipe out everything but the significant figures, right? These zeros to the left disappear. An example I like to present often is population signs that you encounter as you enter a city or leave a city. And I've got 3 examples here. St. Louis shows a population of 856,796. What this implies, as you can see here, is that we know the population of St. Louis, the city of St. Louis, to a precision of plus or minus 1 person. And that's out of a total population of 856,000. Not so far removed from a million people. So that's a striking claim to make. First of all, it's not easy to count 856,796 people. Anything, in the hundreds of thousands of people is not a quick and easy count. I'm not sure how they come up with this number. Let's say it's from census data. A lot of people I know who live in cities that have population signs have never met a census taker. So apparently census people don't come to every door, and they certainly don't do it every year. I think I received a letter from the Census Bureau in the year 2010, because they send out such a letter every 10 years. These signs stay up for often several years. So the idea of counting to say we have made a count and St. Louis has 856,796 people, that's quite amazing. I'm going to say that within the time it took them to count all those people, probably some people died and some new people were born. So that number was changing while they were counting it, probably, and since they've posted the sign, it's changed. Moreover, people move into cities and move out of cities. A big city like St. Louis, who knows how many people have moved in and how many people have moved out, and it doesn't necessarily keep the number exactly the same, certainly not to plus or minus 1 person. Probably, it's hard to say in a population of 856,000 that you know it to within plus or minus 10 people. If this was a 0, and the 0 is just holding the number place, this 6, if it became a 0 and that 0 is just holding the number place, then we would say this number had 5 significant digits.